In today's lesson, we are going to be looking at the length of a line segment. So we're going to be moving on from looking at midpoints to now looking at the length of a line segment. So this is something that we are going to use later on to help us determine some geometric properties and just look at some analytic geometry as well. We're still going to be dealing with lines and graphs and points, but now we're just using that to help us determine lengths. So just as a quick warm-up, determine the length of the line segment below if we're dealing with negative 4, 2, and 6, 2. So negative 4 and 2, I'll just hypothetically put it here, and 6, 2 would be here. And essentially it is a straight line. So how long is that line? Well, an easy way that we can tell is we can just do 6, the endpoint minus the one endpoint minus the other. So our length will be 6 minus negative 4, which equals 10. So that means that this line segment is 10 units long. Fairly straightforward example. Look at a different one. Determine the length of the line segment below, where we're dealing with the point 0, 4, and 4, 4. So again, I'm just going to hypothetically draw that in. So 0, 0, let's put it up here, 0, 0. We have another point, 4, 4. So this one's a little different because this one is now on an angle. But a hint that we're given is draw a right triangle to show the rise and run of the two endpoints. Okay, well if we show the rise, we're going up here. If we want to show the run, this is the run. Our rise is 4. We went from 0 to 4, and our run is 4 because we went from 0 to 4 for the x's. So is there something that we could do here that would help us determine this length? Well, let's think about what type of triangle do we have? We have a right triangle. Do we have anything that would allow us to find this diagonal of a right triangle? If you think back to last year, right, you might have learned about something called the Pythagorean theorem or the sum of squares. And that was a squared plus b squared equals c squared, with a and b representing the two legs and c representing the diagonal or the hypotenuse. So I know that my one leg is 4, the other leg is 4 coming from these two sides, and that will equal c squared. So 16 plus 16 equals c squared, 32 equals c squared. We then need to square root 32 to get c by itself. And when we square root 32, we get 5.6. We'll say 5.66 is equal to c. So that would be the length of that line segment. If we wanted an exact value, right, we probably would leave it as just the square root. So depending on what the question asks, probably won't see this too much, but later on in grade 11 for sure, you'll see something where we talk about the exact value. So we would just leave it in this root form, square root of 32. That's going to be the exact value, because when we take a square root of that number, we're going to have a decimal and we'd have to round and it wouldn't be technically exact. But for our purposes, we can square root it, we get 5.66. So that idea here of if I have any sort of line segment, I can use the rise and run between the endpoints to help determine the length by using the Pythagorean or the theorem or the sum of squares. So that's the idea that we're going to use to come up with our formula. So if we have a random line segment, right, let's just give these random points. We'll call this x1, y1. And here we're going to have x2, y2. If I'm looking at determining, keep it consistent, forming a right angle triangle, I have my rise, and how can I calculate rise? And if we think of the slope formula, or we think of different ways that we can calculate the rise portion, or the numerator, or the top part of our fraction, right? You might think of, I'll just write it out. So rise, right, over run. I'll write it all out so we can kind of see rise over run equal to rise, we might say, is delta y over delta x, which is also equal to, we had a new formula, y2 minus y1 divided by x2 minus x1. So this idea here at the end, this idea looking at this algebraic expression, this is what we can use to help us determine the rise of our line segment. So I can represent the rise as y2 minus y1. And we want to focus on it this way. We don't really want to have to set up a table of values every time. So we want to try to move more into this algebraic method of calculating slope, or of calculating the rise in this case. Our run, similar idea. We're focusing on the bottom portion of this fraction, or of this expression for slope. And for run, we can do x2 minus x1, or basically the change in x will be our representation for rise. Now, we know we're going to use the sum of squares, or the Pythagorean theorem. So if I write that out, a squared plus b squared equals c squared. C squared is representing the length, and a and b are going to be our two sides. Oops. I'll call x a because x does comes first, y will be b. Either way, it doesn't really matter. But I can replace a squared and b squared with, or at least a and b, with these expressions. So instead of a squared, I could do x2 minus x1 all squared, plus for b, I could write y2 minus y1 all squared, and that will equal our length squared. Now, one thing we want to do, if I want to solve for the length, I need to get rid of that squared. I need to get rid of this little portion up here. And how I can do that is by square rooting the entire side, or both sides. One side it'll cancel out, and the other side will stay there. So I can rewrite this as the square root of x2 minus x1 squared plus y2 minus y1 squared, and that will equal the length. So this is the formula that we're going to be using. Oops. Make it a little bigger. This is the formula that we're going to be using going forward when we're dealing with the length of a line segment. So it is a play on the Pythagorean theorem, or sum of squares. This is what we're going to be dealing with. So length of a line segment. Right, so that's the formula that we're going to be dealing with. So let's look at an example, right? We want to determine the length of the line segment, right? We have our formula, distance or length, whatever you want to call it, is the square root of x2 minus x1 squared plus y2 minus y1 squared. I have my points, or I have my line segment, I have my points. If it helps, and I would recommend this at first, label your points, right? So I have x1, y1, x2, y2. Again, it doesn't matter which one you make the second point or which one you make the first, as long as you're consistent. So we have an x2 and a y2. We don't have an x2 and a y1. So just make sure we're consistent with that. So once I've labeled my points, I can sub that in to our formula. So I'm going to rewrite this out and just substitute everything in. So x2 is 3 minus x1, which is -4. That is all squared, plus y2, which is 1, minus y1, which is negative 2. So keep in mind the minus is in there, so when we're minusing a negative, right, we don't just, oh, we already have a negative, so we don't need to include another one. We do still need to include it. So this becomes the square root of 3 plus 4 squared plus 1 plus 2 squared. Just make this root a little bit smaller. D is equal to, or the length is equal to 12 squared plus 3 squared. Not 12, sorry, didn't multiply. 7 squared plus 3 squared. I guess technically length of the line segment, if we're going down, move this below just for sake of room. All we wanted to do in the first one is just substitute our points in, make sure we were comfortable doing that. Once I go through and calculate, I get D is equal to the square root of 49 plus 9. D is equal to the square root of 58. Again, that's my exact value because when I go to square root it, I do not get a nice answer. I get 7.62. But again, for our purposes, it's okay to do that square root to get an answer. Later on, different courses next year, you might need to find the exact value. So again, we're labeling our points, we're plugging it into our formula, which is a modified version of the sum of squares formula or Pythagorean theorem, and then we're going through and calculating. Next example, determine the length of a line segment with endpoints G, which is 4, 3, and H, which is 2, negative 2. So I don't even need to draw this out because I'm looking for the length of a line segment. I am going to relist my points just so that I can label them x1, y1, and H will be x2, y2. We'll do that in different colors just so it's easier to see. x1, y1, x2, y2. Again, it doesn't really matter which one's which, as long as we're just consistent. So now I can look for my length. So I can call it GH. So GH, or the length of GH, is going to equal the square root of x2 minus x1 squared plus y2 minus y1 squared. I'm going to plug in my values. x2, so 2 minus 4 squared plus negative 2 minus 3 squared. Make sure when you're squaring these, right, when we simplify the brackets, first we get negative 2 squared plus negative 5 squared. Make sure you put the brackets around the negative. You don't want to do minus, keep the negative outside because you may get the wrong answer. We are squaring, so all of our answers should end up being positive in this case when we go through and add, because it makes sense. We can't have a negative distance, right, or a negative length. We can't say a line segment is negative 4 centimeters long. That wouldn't make sense. So make sure whenever you square your numbers, you should end up with a positive value, regardless of whether, regardless of what the initial value happens to be. It should always end up being a positive value. So negative 2 squared is 4, plus 5 squared, which is 25. I end up with the square root of 29. That would be my exact value. I could leave it as that, or the square root of 29, which gives me 5.39. That is rounded. So again, that is why we call the root one the exact value. This because we don't worry about any rounding errors or rounding too short. But either way, the length of the line segment is 5.39. Last example, a plane is flying from Toronto to Halifax. When the plane is at coordinates 125, 309, the plane develops engine trouble. Ottawa International Airport is at coordinates 97 to 215, and the Pierre Elliott Trudeau Airport in Montreal has the coordinates of 39 or 139, 412. Which airplane should the plane divert to? So basically, which one is going to be the shortest distance? So basically, this is just two line segment questions in one. We're just going through and calculating the two distances and seeing which one is shorter. Right, so we're going to call this, let's call the plane coordinates x1, y1. And the other ones, we can call them x2, y2. We can call them x2, y2, both of them x2, y2 for our purposes, because in our formula, we only have 2 points. When we go through and do the calculations, we could say the distance to the Pierre Elliott Trudeau. So that's going to signal the difference when we plug in our points. And we'll do another one that's the distance to Ottawa. So again, I'm just going to write out our formula, x2 minus x1 squared plus y2 minus y1 squared, all under the square root. Same thing for the distance to Ottawa, x2 minus x1 squared plus y2 minus y1 squared. I'm going to go through, I'll do the Pierre Elliott Trudeau Airport or Montreal Airport first, and then we'll do the Ottawa one second. So x2, we have 139 minus 125 squared plus 412 minus 309 squared. 139 minus 125, we get 14 squared plus 103 squared. Just to make sure we're doing our calculations right, I'll go through and do the extra steps. So 196 plus 10,609 equals the square root now of 10,805, which I get as 103.9. For Ottawa, again, doing the same calculation, just with different values. So x2 now is 97 minus 125 squared plus 215 minus 309 squared. Right. Again, you might think, well, that doesn't quite make sense in terms of where the plane is located. Technically, Ottawa should be behind it, and that's true. Again, this is just more for a reference of just visually, or just to see the different line segments. Right? If we wanted to be accurate, technically that Ottawa point would be behind the plane, right? So the plane is either turning around or going forward. But we're just looking for the distances, so I just wanted to visually see the two distances or see the different values. So when I go through, we have negative 28 squared plus negative 94 squared. Even though these numbers are negative, we should still end up with a positive due to the squaring. So we get 784 plus 8,836. Get 9,620. We have to square root, and we get a rounded answer of 98.08. So comparing the two distances, we can clearly see that going to Ottawa, or the distance to Ottawa, is shorter. So therefore, the plane should go to Ottawa. So again, this is just kind of taking the sum of squares or Pythagorean theorem, incorporating our points or our rise and run kind of calculations into it to allow us to calculate the length of a line segment. You can kind of see how this calculation could be used in the real world. Basically, coordinates could be coordinates on a map or coordinates on GPS or longitude and latitude. And we can use that to kind of help us map distances or calculate distances. So if you think of using a GPS or using Google Maps or Apple Maps, it's that general idea where it's probably doing these calculations in the background very quickly and using that along the road to basically determine your distances. But just make sure you are comfortable with these calculations, with this formula, and understanding a little bit of how the formula is made. Because if you understand how we came up with the formula, that can help when you are using it.